In this video, we're going to be looking at inscribed angles. So we're going to go over what exactly those mean in terms of our unit involving circles, and I also have 3 theorems that we're going to look at that involve inscribed angles. So before we dive into any of those theorems, I want to look at this circle here. I'm going to label it circle K. And what we have is, if I label this point C, we have 2 chords. We have chord AC and BC. Now, we know that they intersect at this point right here because we can visually see it, and we can also see when I write down the names of these chords that they share that point. So inscribed angles are essentially 2 chords that intersect at a point, and when we look at those 2 chords, we can see that we create an angle. So the vertex of that angle is lying on the circle, and then the other 2 parts of the chord are going to intersect on the other side. And so what we get when we look at this first theorem involving inscribed angles is that we have a relationship between the inscribed angle and also the arc that is formed by the intersection, in this case on points A and B. So the arc that is made by points A and B is right here. We would simply call that arc AB. And what we're going to see is a relationship between the measurement of the inscribed angle and also the measurement of the arc, which you can see I have right here. So if I'm given the measurement of arc AB, let's say that's X degrees. If I want to find the measurement of the corresponding inscribed angle, all I would have to do is take the measurement of arc AB and divide it by 2, or in this case, multiply it by 1/2 to get the measurement of the inscribed angle. Now, in the opposite direction, if I'm given the measurement of angle 1 in this case, and I want to find the measurement of arc AB, what I can do is take the measure of angle 1 and just multiply it by 2. So what I want to do is look at an example of when we're given certain bits of information about circles and their inscribed angles, how we can use this theorem to find what we need. So looking at my first example, I have this circle right here, and it wants me to find 2 things. It wants me to find the measurement of angle X and also the measurement of arc YX. This here should have a little arc symbol over it. So looking at the measure of angle X, I'm actually just going to leave that as, let's label that as A, just so I don't have to carry around the measure of angle X with me. So looking at the measurement of angle X based off of the inscribed angle theorem, what I can do is take the measurement of this angle, multiply it by 2 to get 86 degrees. So I'm going to go ahead and set up a formula that's going to give me the relationship between the inscribed angle and the arc that I just stated. So if I look at the measurement of angle X, what I just stated is that I can take this arc measurement and multiply it by 2 to get the measurement of arc ZW. So here I said that the measurement of angle X was A, so I'm going to substitute in angle X with just this variable here. And I still have that that's equal to arc ZW. Now, I also know the measurement of arc ZW, so that's where I'm going to be able to replace the measurement here with the actual degree attached to it, and then I can just solve for the measurement of angle X. So I can say that 2A equals 86 degrees. And here I can just use simple arithmetic. So if I'm multiplying by 2 on the left, I would have to divide by 2 to get A by itself. So dividing by 2 on the left just gets me A, and 86 over 2 is just 43 degrees. Now, A is my replacer for the measurement of angle X, so I would want to rewrite this as the measurement of angle X equals 43 degrees. Now, something I want to point out is that I used this second formula. That is simply because of my comfort level is that I always like to have, I don't want to have to deal with fractions unless I have to. So I simply always use this and then just solve. However, it probably would have been a little quicker just to say that the measurement of angle A is 1/2 of the arc. So erasing this real quick, if I had used my first formula, I would have said that A equals 1/2 the measurement of arc ZW. I know that arc ZW is 86 degrees. And so if I take 1/2 times 86, I get 43 degrees. So this is actually a little quicker, but either formula is going to get you the right answer. It's just that one is solved for the angle and the other one is solved for the arc. So now looking at the second part of my example 1, it wants me to find the measurement of angle YX, which is right here. So before I plug anything in, I just want to state the relationship between the inscribed angle and the arc. So looking at my diagram, I can see that the measurement of angle Z is going to be twice the measurement of my arc. So plugging in here, I know that the measurement of angle Z was 52 degrees. This here is a 2, it kind of looks like a Z, so let me switch that. 2 times measurement of angle Z was 52 degrees equals the measurement of arc YX. And so here I can simply simplify because I know that 2 times 52 is 104 degrees. So here, since I was solving for the measurement of the arc, it was quicker to use my second formula right here. So moving on to my second theorem, we're going to look at multiple inscribed angles that are all intercepting the same arc. So if I look at my diagram, I have this green arc AD, and I have 2 inscribed angles, angle B and angle C. What we're going to see is that it doesn't matter where the point of the inscribed angle lies on the circle, as long as it intercepts the same arc, they're all the same measurement. So here I have angle B and angle C intercept arc AD, the same arc, so their measurements are going to be congruent. So I could take an angle and I could drag this point anywhere I wanted to. As long as my endpoints were at A and D, I'm going to have the same measurement on all of the inscribed angles. If we want to look at that in action, my example 2 here, we're going to go ahead and try and find the measurement of angle R. And looking at what I'm given, I have 2 inscribed angles, and I'm going to make them different colors so that they're a little easier to spot. Because right now it kind of looks like I just have a bow tie on top of my circle. So this is going to be my first inscribed angle, angle S, and my second inscribed angle is angle R. And what we have here is the same exact situation we had in this diagram up here, where they're both intercepting arc TQ. So since we know they're both intercepting arc TQ, we can state that by theorem 10.7, they're going to be congruent, the measurements of angle R and angle S. So if I were to state that using symbols, I would have that angle R is congruent to angle S. So since we know they're congruent, we know that the measurement of angle R equals the measurement of angle S. I only have expressions with a variable x. I can simply set them equal to each other and solve for x to find the measurements of not only angle R, but also angle S. So I know that the measurement of angle R is 12x minus 13, and the measurement of angle S is 9x plus 2. So here I can just use some simple algebra to solve for x, and so I want to get all of my x's on one side and all my constants on another. So I'm going to start by subtracting by 9x on both sides. On the right, 9x minus 9x cancels. 12 minus 9 gets me 3x, and I'm going to carry down my negative 13, carry down my 2. And so now, since my x's are on the left, to further simplify, I'm going to want to add 13 to both sides. On the left, negative 13 plus 13 cancels, and I can bring down my 3x. And then 2 plus 13 on the right is going to give me 15. And so to finish off, since I'm multiplying by 3 on the left, I want to divide by 3 on both sides to undo my multiplication. So 3 over 3 gets me x on the left, and 15 divided by 3 gets me 5. Now, it's tempting to say we're done since I solved for x, but my question was actually asking for the measurement of angle R. So what I need to do is go back, plug in x into my original equation for angle R, and find the degree value attached to R. So the measurement of angle R we knew was 12x minus 13. And so since I knew that x equals 5, I'm going to get 12 times 5 minus 13. And to fully simplify, I know that 12 times 5 is 60, and 60 minus 13 is 47 degrees. All right, so we have one final theorem to talk about, theorem 10.8. These theorems don't typically have names, so I have a number assigned to it, but really we're just going to know how to apply these concepts in general instead of assigning theorem names. So we're going to look at one final inscribed angle, but in this situation, we actually have that the points of the inscribed angle are going to intercept the diameter. So in words, we have an inscribed angle of a triangle intercepting a diameter, and we know that this happens if and only if the inscribed angle is a right angle. So in this particular situation, we have arc FJH, and we use that extra point here so that we knew that we were talking about the bottom half of this circle and not the top half. So because we know that FJH was a semicircle, since that's given, the corresponding inscribed angle with it is going to be 90. Now, if I drew another point right here and called it K, say I was looking at angle FKH, would also be 90 degrees. So it doesn't matter what inscribed angle we have, as long as those points intercept that arc FJH, we're still going to have 90 degree angles consistently. And then in the opposite direction, if we have an inscribed angle and the measurement is 90 degrees, then that means the arc that is corresponding to that inscribed angle is going to have to be a semicircle. So we're given two pieces of info here. This theorem exists essentially because of the first theorem we talked about, because what we have is a relationship between the arc and the inscribed angle that is going to give us the measurement of the semicircle here being 180 degrees. If I'm given this arc, FJH, my first theorem told me that if I take that arc and divide it by 1/2, then I would get the measurement of angle G. So naturally, if I'm given, like in this scenario, that FJH is a semicircle, we know that all semicircles are 180 degrees. So I can replace FJH with 180. And then on the left here, 180 divided by 2 is going to get me 90. So to prove this, we would actually end up using the inscribed angle theorem. So looking at this final example, we're going to go ahead and apply what we just learned. So here I have diameter AB, and I have an inscribed angle C, and I can tell that angle C is going to intercept diameter AB. So that means that angle C would have to be 90 degrees. Now what's nice about the relationship with inscribed angles that intercept the diameter of a circle is that we can see we actually get a right triangle here. If we take this inscribed angle and then connect both of the points with the diameter, then we can use properties of right triangles to further solve what we're trying to find. So what we are trying to find here is angle B. We can use properties of right triangles to do that. What we can do is use the angle sum theorem, which means that I'm going to add up all of my angles and set them equal to 180. So what I can do is take the measurement of angle A plus measurement of angle C plus the measurement of angle B equals 180. So now doing some substitution here, I know that angle A equals x plus 4. Measurement of angle C was 90 degrees, and the measurement of angle B is 8x minus 4. So from here, all we want to do is combine like terms and solve for x. And then once we know x, we can plug it back in to find the measurement of angle B. Looking at some terms I can combine here, I have x and 8x to get me 9x. I can combine 4 and negative 4, but actually I just get 0 here, so I get a cancellation. And so I'm just left over with 9x plus 90 equals 180. So now to solve for x, I want to subtract over my constants, so I can subtract by 90 on both sides. So I'm left with 9x on the left, and 180 minus 90 is still 90 on the right. And then to finish off, I can divide both sides by 9 to fully solve for x. So 9 over 9 is 1. I get x on the left, and 90 divided by 9 is 10 on the right. So now looking at back at measure of angle B, since I know that x equals 10, if I want to solve for measure of angle B, I can just substitute in. So 8 times 10 minus 4. 8 times 10 is 80, and so 80 minus 4 is 76. So my answer is 76 for this problem. And I just want to note one final method to solving this equation. It's very similar to the first one I used, but we also could have skipped straight to setting the measurement of angle A plus the measurement of angle B equal to just 90 degrees. And the reason we can do that is because we learned that when we have the remaining two angles that aren't this right angle C, we have that they're complementary. Because if the whole entire triangle adds up to 180, if I subtract 90, naturally A and B will have to be equal to 90 to get to 180. So substituting in for measurement of angle A, we again would have gotten x plus 4, and measurement of angle B is 8x minus 4 equals 90, and so we'll still get x equals 5, but we have a little bit less to work with, so we could have solved straight from here if we wanted.